Alright, so something that I think you should know is about conservative and non-conservative forces. So conservative versus non-conservative. So forces. So what that means is, say, so conservative forces is independent of position. And non-conservative forces is dependent on position. So what that means is, say if I have a ball, right, and I drop it. So then, like, let's just draw the next stage. So this is stage one, and stage two, and then I pick it up and drop it again. There's no um, when you keep dropping it over and over and over again, no matter how many times it goes up and down, up and down, up and down, the change in potential energy is always the same, no matter what. So that's what it means by a conservative force. So it's so basically, no matter how far you put it back and forth, it's always going to be the same. But when we're talking about non-conservative forces, say if you have a box, right, and then you're pushing it back, and then force on a like a very very rough surface. When you do that, you actually feel it getting warmer and warmer and warmer and warmer. So basically, when you're doing it back, when you're putting it back and back and forth, back and forth, back and forth, even if like the displacement is zero, or like you're pulling pulling it back and forth the same distance, there's an increase in thermal energy. You're gaining more and more heat the more you put it back and forth, back and forth, back and forth, back and forth. So that's what it means as a non-conservative force. It is dependent on distance and position. So basically, we can redefine the network on a system to be the conservative forces plus the non-conservative forces. So, like, conservative forces are like work done by like a spring or gravity, like, you know, and that those relate to gravitational potential energy and elastic potential energy. But non-conservative forces are like friction. So basically, like, say like for like gravitational potential energy, so work conservative would just equal the negative change in potential energy. Right? Because usually, like, the gravitational potential energy is going the opposite direction of motion. Alright, no, not the opposite direction, but it's usually going down. And then basically when we sub that into like, so we know the network is the change in kinetic energy. So we basically can say when we sub both of these in, so the change in kinetic energy is equal to the negative potential energy plus the non-conservative force. And let's just say it's frictionless. So let's just, and we can just cancel it out. So add PE to both sides, and you get KE plus change in plus PE. And then look at that. That is the same thing as the change in total energy. But that's beyond the point. So let's erase this. And remember, since this is 0 and then you're adding P to both sides, those cancel out, that'll just be 0. So if we rewrite this as like the original form, actually let me just do it by KE and P. So KE F minus KE I plus PE F minus PE I equals 0. So we bring the initial energies to the right side, so we get KE F plus PE F equals KE I plus PE I. And this looks pretty much exactly like the conservation of energy. So using non-conservative and conservative forces, we can basically prove that this is true. And then say like if this wasn't frictionless, let's say this actually had an actual value. So then we can basically say that the change in kinetic energy and the change in potential energy is equal to the non-conservative work done. And then basically rearrange it. So yeah. So what we can also do is like since these are a lot of these are like conservative forces, they're usually potential energy because kinetic energy is like the energy of motion. So it's really it really doesn't have a force for it. It's caused by a force, but it's not a force itself. But potential energy has the potential to make energy, and when it does, it creates a force. So what I mean by that is like the force of gravity is the same thing as mg, and Hooke's law says the force of the spring equals kx. So basically, if we're trying to do the work, if we're trying to have the work done, see, these are conservative forces. So if we're trying to derive the work done, you just integrate both sides with respect to dx. So basically, you get the work done by gravity equals mg delta x, right? Because if we're applying the boundaries terms, like right here, and then the work done by the spring is the same thing as not m one half, because there's already an x. There's already x in the equation, so you add power to that and divide by the same power, so it'll be 1/2 k delta x, right? Because it's being evaluated at x2 and x1. So, and this is the same thing as the potential energy, right? The change in potential energy. Or we could say mgx, and then us equals 1/2 k x squared. So with with um with basically these formulas, we can find force by um, taking the derivative with respect to x. So work, so that'll be the same thing as du equals mg dx, and then du equals 1/2 k x, or more specifically 1/2 kx squared dx. And oh, I forgot x here. So when we're taking the derivative of both sides, get so when you evaluate this, this should be du equals mg, and then du equals kx, and then don't forget dx. Don't forget dx. So we can divide dx by on both sides. To get du over dx equals mg, and then du over dx x equals kx. And that is the same thing as our force of gravity and force of spring. So that basically what it's saying is the derivative of potential energy with respect to position is just force. This is like pretty useful when you're given like a graph or a function and you're trying to find the force, and then you can find like acceleration. For example, you can basically take the derivative of that function with respect to x if it's like a potential energy function, and then you can use F equals ma.